Okay, for the climax of Chapter 8, I want to talk about systems of ODEs. And to start off with, let's do a topical example, the SIR model of epidemics. Right? This is a good example also of why you might want to have systems of ODEs. The point is that you might have several quantities that you're interested in that all depend on the same independent variable. For example, time. Right? So that's what happens in an epidemic. You have three cohorts of the population, those who are still susceptible to the infection, those who are currently infectious, and those who have recovered and are now immune. Right? Those are three important distinct categories that we have to keep track of, and they all vary over time. And the rate at which they change depends on each other's values, right? So the more susceptible and infectious people there are, the faster the infectious people will be growing, and the faster the susceptible people will be falling in number. So this is a very simple model, by the way. Real epidemiologists do much more complicated stuff, but this is still good enough to give you a pretty good idea of what goes on in an epidemic. And you can see some of the things people have been talking about with respect to the coronavirus. Let's see. So, basic idea is that it's when susceptible people and infectious people meet, when you have these two categories of people meet, then there's a possible spread of the infection, right? A susceptible person might catch the infection. So therefore, the rate at which the susceptible people, or the number of susceptible people is growing, will be proportional to the product of S times I. Right? The bigger either one of these numbers is, the faster the infection will spread. And then there's some constant of proportionality here, C, and that basically corresponds to the growth rate of the illness. This is similar to, but not quite the same as R0. You may have heard people talking about R0, which is the number of people that one infected person can in turn infect. This C is similar to that, but it's the rate of infection per day. So, for example, with coronavirus, I think there are estimates like one infected person might infect maybe 3 or even more, maybe 3.5 people, and then but that's over the course of the illness, which might last for 15 days. So that would work out to a growth rate C of approximately 3 divided by 14 or 15, about 0.2. Right? Oh, by the way, this is negative because as the infection spreads, the number of susceptible people goes down. Right? Once a susceptible person becomes infected, they're no longer considered in the susceptible category. On the other hand, the number of infected people goes up by the same rate. Right? Every time somebody becomes infected, they move from S to I. And so the same term here is positive for the derivative of I. On the other hand, infected people will, with time, recover and become immune. And so we have to subtract off the rate at which they recover. And we're assuming that's going to be some constant times I. So D is like the recovery rate of infected people. The people who are recovered come exclusively from that source. They come from the infected people who have recovered, so the rate at which the recovered people grows is simply DI. Okay, so that's the basic SIR model. It's kind of worth pointing out how strange this whole picture is. In reality, infectious diseases, epidemics, they are discrete things, right? People are discrete things. You can't have a fraction of a person. You can't measure people, using a continuous variable. So we only use calculus to model human things like this because it's simpler, right? It's actually simpler to use calculus to model human things like this, like epidemics, than to try to do it by working with whole numbers, right? On the other hand, now that we actually have to solve a differential equation, it's simpler to then work with numerical methods. So we've kind of gone full circle. We started with a discrete problem in the real world, right? Where all these numbers, Si and R, they're all discrete values. We imagined they were continuous in order to use calculus to model them, so we modeled them using these differential equations. But then to actually compute an answer, we go back to the discrete method, basically, and we use numerical methods on a computer to try to solve the differential equations. And, you know, the numerical methods are basically discrete methods that there's a limit to how finely you're able to distinguish numbers on a computer. There's really only a finite number of numbers you can represent on a computer. So when you do something on a computer, you're really doing it in a discrete way. So it's a little bit strange. It suggests that maybe it would be better, and I think this is what real epidemiologists do, maybe it would be better to just work with a discrete model to begin with. And if you were in my 447 class, you may have done that. We talked about discrete models of things. Okay. Well, I have some good news. Working with systems of differential equations is actually just as easy, or almost as easy, as working with just a single differential equation, because we simply replace the single equations with matrix equations. So, for example, in this case, with the SIR model, SIR model, what we do is we let our dependent variable be a vector where the components are S, I, and R. And then the differential equation will say y prime. Note that y prime itself is going to be a vector here. It will consist of the derivatives of S, I, and R. That will be given by a vector function, or a function of time and the current SIR values stored in the vector y, which simply returns a vector consisting of the formulas for the derivatives, right? So the formula for y, S prime, the formula for I prime, the formula for D prime. So all you really have to do is go back, I'll show you on the next slide, but you really only have to make a few minor modifications in order to change the MATLAB code so it'll deal with matrices and vectors instead of just scalars. Also, the function I'm going to use, the MATLAB function I'm going to use is the AM2sys function. So this is the Adams-Moulton method with 2 points, having been tweaked to accommodate systems of equations. So I just changed things so it would deal with matrices and vectors. And remember that the 2-point AM method for systems, the 2-point AM method, I should say, is essentially the same as the trapezoid method. So I commented on that in the previous video that if the AM system does a linear interpolation between 2 points. So if you do a linear interpolation between the previous point and the new point, you're basically doing the trapezoid method. The code for AM2sys looks a lot like the trapezoid method. It's really, I could have called it the trapezoid method, but I was borrowing code from Atkinson and I just kept the same name. Also, it's done with just a single iteration, and as we saw previously, using the trapezoid method, even with a single iteration to solve the implicit equation, is good enough to get you to second order convergence. So that's all I did. So let's see. So here's the AM. This is the business part of the AM2 system function. Let's see. What should I mention? Notice that we have I modified this line of code because now the y values are vectors. So the first index here tells you the time, or basically the time index, and the second entries, these are going to be the indices for the different y values. So, for example, in our case, it will be the S, I, and R values. And so I just had to basically replace y wherever it occurred by an expression like that, right? So to accord with the fact that y is a vector, right? So in all these places, y is now a vector, here too. And then let's see, anything else that's different? Let me just point out also that as I said, we're using the iteration method with one iteration to solve the implicit problem. Right? We're looking to solve for, or to get a good estimate for the new y value, y sub I. And what we do is we take an initial guess that the y value is simply the old y value plus the slope determined at the old point, right? Using the value of f at the old point. That's what ft here is. It's just the value of f at the previous point. And then we use that estimate to get a new estimate for the value of f at the new point, right? So we use this estimate to get the value of f at the new point, and then we average those two values. So the value of f at the old point and our estimate for the value of f at the new point, we average them. This, of course, will not be an exact solution, but it'll be close enough. And then that's what we multiply h by to get our change in y to go to the next point. Okay, and then so then this becomes the final definition for yi, and then we take our new f value and call it the old f value, right? So we're cycling through the f values, and then we can repeat the loop. Okay. One other thing that's worth pointing out about systems of ODEs is that you can also use them to solve higher order ODEs. So, for example, suppose you wanted to solve this equation, z double prime equals minus 2z. Well, you might be able to guess what the solution is to that, actually. It's definitely a well-known function that you know. So, but what we can do is, even though this is a second-order differential equation, it's still just an ordinary differential equation. So we're assuming z is simply a function of x, but it's a second-order derivative that we're working with. So the trick is, what you do is you introduce this new variable u, and u is going to simply represent z prime. So u is almost a dummy variable that we just introduce into the problem in order to represent z prime. Then we can say that, well, the derivative of our variable z is equal to u. And then the derivative of u is minus 2z. And this is where we've encoded the actual differential equation we wanted, because the derivative of u is the derivative of z prime. This is z double prime. So this says that z double prime equals minus 2z. And so we were able to kind of sneakily smuggle in a second-order differential equation in the guise of a first-order system of differential equations. Right? So it's a neat trick. And when I set this up, and I will do both of these problems on MATLAB in a minute. So y will be a vector that consists of the z and the u value. And then the function f of x capital Y will be a vector function that returns u for the derivative of z and minus 2z for the derivative of u. Right? And so it will, we will have the ODE in exactly the same form as usual, y prime equals f of xy. Okay, let me switch over to MATLAB. Okay, so let's model the spread of an epidemic using MATLAB. So let's see. I think for our case, oh, by the way, let me point out what I'm going to do is instead of measuring the size of these three groups, the susceptibles, the infectious, and the recovered, in terms of number of people, I'm just going to measure them in terms of a fraction of the population. So we'll say that the total fraction is 1, and then each one will be a subgroup, and all three components will then add up to 1. Okay, so I'll start off by saying that our initial number of susceptible will be almost everybody. Let's say like 99.99% initially are susceptible, and the initial number of infectious is just a tiny handful of people, so 0.001. right? So we have just a very small group that's become infected initially. And then we'll say that R0, the number recovered initially, is 0. Nobody's recovered yet. Okay? So then our Y0, the initial Y vector, is S0, I0, R0. Oh, by the way, on MATLAB, these are going to be row vectors. In the notes, I wrote them as column vectors. Not really a big deal. Just have to remember when we're working with MATLAB, they're actually going to be row vectors. Let's see. Now, I should define the function I'm going to use. Let me see where I got this. Yeah. First of all, let me define my constant c. So c is the growth rate. That was going to be 0.2. Right, because it's about 3 people over the course of about 15 days, so that works out to about 0.2 people per day initially. And then for D, the recovery rate, I think they're usually saying, again, it takes about 2 weeks to fully recover. So I'll just round that off to 15 days, and we'll say that D is about, no, actually I rounded up to about 20, right? So I said, supposing it takes on average about 20 days to recover, then D would be about 0.05. So maybe that's a little bit low. On the other hand, people who become seriously ill can have it for many weeks. So maybe on average 20 isn't such a bad guess. Anyway, let me go with those numbers, and then let me redefine F again. So F, as you can see, is simply taking the growth rate, negative c, the growth rate times y1, the fraction of people who are susceptible, times the fraction of people who are infectious, right? And then the rate at which the infectious are growing is similar, except we subtract off the number who are recovering, and then the people who have recovered grows only by infectious people, which is Y2, the second component of Y, recovering. Okay, so that's F. Let's see, have I got everything in place here? Then I should be able to, okay, let's try it. So the function returns a pair of lists. So the first list, I'm thinking of the x variable, so to speak, as time, so I'll just call it the t is the time values, and the others will be the y values. And we use am to sys. In fact, do I have this? Yeah. We'll start at time 0. The initial y vector is y0, which we defined above. We'll run it for about 200 days. I think that's enough to get a good idea of what's going on. And I'll use h of 0.1. I think we saw that seemed to be adequate to get a good, reasonably accurate approximation. And we're using our function f that defines the ODE, right? That y prime equals f of ty. Okay, let's try it. What happened? Ah, there we go. Okay. Ooh, that didn't take long. Okay. And now let's plot it. So the t's, yeah, there we go. Ah, good. Okay, good. That's a nice classic epidemic curve, isn't it? So the red line is the people who are infectious. And that starts off close to 0. It grows to a peak, which is a scary peak, where 40% of the population is infected. Wow, after about 70 days, 40% of the population is infectious. And then it drops off. It runs out of fuel, basically, because the blue curve is the number of susceptible people. By the time you get to 70 days, the number of susceptible people has dropped quite far. Everybody's either sick or recovered from it and therefore immune. So the epidemic has run out of fuel. The yellow curve is the recovered people, right? It starts out at 0 and eventually reaches almost everybody. Now, you can see that this is a dangerous situation from the point of view of public health. If 40% of the population comes down with the virus, and of those, maybe 1/5 of them are going to be seriously ill, that's about 8% of the population who are seriously ill and will need medical care. That's going to overload any health system, right? I don't think any health system in the world is prepared to deal with 8% of the population simultaneously requiring, serious care. So the way to deal with this, the way we have dealt with it, is we've tried to artificially lower the growth rate of the curve by isolating, right? So people are gone into lockdown, and that, in a sense, lowers the growth rate from about 0.2. I'm going to estimate that it cuts it by about a factor of 3. So here's what I'm going to do to model the lockdown. I'm going to say that I'm going to define an IR function. Okay, let me explain this. The IR function is going to be a function of t. Now I have another IR underscore fun function that actually calculates a value of t depending on what t is. So the way this works is the first entry is how you split up the time. In this case, I'm saying we're going to split the time up into, I'm sorry, I actually don't want this one. I think I want the one before it. Let me try it. Yeah. That one. That's good. Okay. So in this case, what we'll do is we'll split the time up into the time before day 30 and the time after day 30. And then the numbers in the second list here tell us what the infection rates will be in each of those time periods. So in the first 30 days, we'll assume the infection rate is C. And after 30 days, we'll assume everybody goes into lockdown and the infection rate becomes C over 3, right? Reduced by a factor of 3. So IR, I'm making this a function only of T. So for example, when I enter this, if you check the infection rate at, for example, on the third day, it's going to be 0.2. But if you check the infection rate on, say, the 70th day, it's going to be the reduced lockdown rate effectively of about 2/3 or a third of 0.2, right? So 2/15. So let's see. So what I'm going to do then is I'm going to rewrite F by replacing all of these C's by IR of T, the infection rate at time T. Right? So now C itself is a variable. That's no problem. We can easily adjust the differential equation to handle the infection rate varying over time, because time is one of the inputs, right, to the function f. So I just replace C by IR of T. And now we can try solving the differential equation and plotting. Oh, I should put the hold on. Let me do that. And then let's plot it. And let's see what we get. Ah, there we go. Okay. So now, let's see if I get this. I think the green curve down here is the infection rate, or the number of infectious people with the lockdown. So in this case, it never gets very high, right? The highest it seems to get, it seems to peak around here. What is it? It's about 4%. So about 4% of the population gets infected at the peak. And again, if you're only at 1/5 of that, that's about 0.08% of the population would then be seriously ill, and presumably a health system could cope with that, right? If only 0.8% of the population is seriously ill. So the point of the lockdown is to prevent the peak of the infection rate from being too high to overwhelm the hospitals, right? And then we can see that everything is slower under the lockdown, right? That the blue curve here, let me see if I got this. Yeah, the blue curve here seems to be the number recovered. That's rising gradually throughout, and the purple curve is the number of susceptible people, and that's slowly falling over time. So everything seems to be slowed down that way. In addition, I think, I could have extended this beyond 200 days to get a better picture of the, what happens in the long run. But you will find that fewer people overall will become infected, but at the price of everybody remaining in a lockdown indefinitely, right? So people are now talking about, gee, maybe we should, now that we've, kind of suppressed the infection for a while, maybe we should rescind the lockdown, right? So let's see. Let me try to model that. Let me go back to my IR function. Yeah, and let me do this. Let's suppose that that we, after a lockdown of, say, 60 days, we then end the lockdown and we let everybody return to normal life, right? So I'm modeling that here by saying now the infection rate is going to have two dividing points in time, at 30 days and at 90 days. At 30 days is when we impose the lockdown, and at 90 days is when we remove the lockdown. And then the infection rates on each of the three periods that are created. So on the initial period, the infection rate is C. On the middle period during the lockdown, the infection rate is C over 3. And then after the lockdown is removed, the infection rate goes back to C. Okay, so let's try that. And now let's, I have to redefine F. I often forget to do that. Now that I changed IR, I have to also just redefine F. And okay, let's do the model now and plot it. What does that look like? Okay, so here, this blue curve here is what happens after you remove the lockdown, right? So notice the blue curve was following the green curve up until day 90, but then the infection started to explode all over again. And although at the point when the lockdown was removed, there were more recovered people, right? The blue curve, this blue curve, or the red curve in the new version. This is really confusing, isn't it? But there were more recovered people and there were fewer susceptible people. So here the susceptible people was up here. That means that the peak after the lockdown is removed is not quite as bad as what it would have been without any lockdown at all, but it's still unacceptably high. It's still over like 35% of the population. So, in fact, you cannot simply remove the lockdown after a certain period unless you have some other way to artificially reduce the effective infection rate, right? So one of the substitutes that people have proposed for the lockdown is to do better testing and tracing people who become infected. That might very well work, but we'd need to have lots of tests that are easily available to test a large part of the population in order to be able to know who's sick and who isn't. And then that might effectively allow us to lower the infection rate, right? If we can see who the infected people are and we're not just working blind. Okay, let me remind you, I am not an epidemiologist. I just had too much fun playing with these models. These are very crude models, as I said. Real epidemiologists do much fancier models, much more complicated stuff. But I think it's interesting that even this simple model gives you a reasonably good picture of what people are talking about in the news, right, with the infection rates and susceptibles and everything. Okay, now let me do the other example. I was also going to do the example with the second-order differential equation. So we wanted to try to solve the second-order differential equation, z double prime equals minus 2z. Okay. Did you figure out what the solution is? You'll see it. So we were going to formulate that by saying, let's see, let's let y, let's say that initially y is, I'm saying y is 0. Remember that in the y vector, the first entry is the z value, and the second entry is the u value. So the initial z value, let's just say we start off at 0. And let's assume, I have my reasons for doing this, which you'll see in a minute, but let's just say that the initial value for the derivative is minus square root of 2. And so this is the initial u value, and remember u represents z prime. So I'm going to use that as my initial first derivative of y. Okay. Now, what is the equation? Let me call this one g. So g will be, let's see, g will be right. So g will be, says that the derivative of z, that is the first derivative of z, will be the second entry in y. That is u, right? U simply represents the first derivative of z. But the derivative of u will be equal to minus 2 times the first entry in y, which is just the z value. Okay? Oh, by the way, I think I wanted to... oh, yeah. Okay. Let me do that. I don't think I wanted that negative here. Let me get rid of that. Okay, let's try that. Now, I think we can solve this now. Let's see. So in this case, well, we do have x's and y's. So x's and y's equal to, there we go. I'm going to use the same function, the am2 sys function. We'll start at 0. We start off, I could just write y0 here. We'll start off with our y0. I'm going over a length from x equals 0 to x equals 2 pi. There's another clue as to what the solution to the function is. And we'll use h as 0.1, and we'll use g defining our differential equation, right? That y prime equals g of xy. Okay, let's try that. Okay, let's plot it. X's, y's. There we go. Now, do you see what the function is? The blue curve is the is our z, and gee, that looks an awful lot like a sine function, doesn't it? Yeah, in fact, g is a sine function. And the red curve is u, which of course is z prime. If z is the sine function, then u is the derivative of z is some cosine function. Now the constant of 2 comes in there, so actually what z is, it's sine of square root of 2x. So we get this factor of radical 2, and that's why the derivative would be radical 2 times cosine of radical 2x, and that's why I set the initial value for the derivative to be square root of 2 up here. But it worked. It did exactly what it should do, right? It found the correct solution for that. So incidentally, this differential equation, when you say z equals minus z double prime, that's a basic definition of harmonic motion. So that's a big thing in lots of areas of math and physics, harmonic motion. But when the second derivative is proportional, well, but opposite in sign to the original value of the function, that's harmonic motion. Okay, hope you had fun.